The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
We introduced the data last time. These were some macroeconomic variables that can be used for forecasting the economy in terms of growth and factors such as inflation or unemployment. The case note goes through analyzing just three of these economic time series: the unemployment rate, the federal funds rate, and a measure of the CPI, or Consumer Price Index. When one fits a vector autoregression model to this data, it turns out that the roots of the characteristic polynomial are 1.002, then 0.9863. And you recall when our discussion of vector autoregressive models, there's a characteristic equation sort of in matrix form that determines just like the univariate autoregressive case. And in order for the process to be invertible, basically we need to have the roots of the characteristic polynomial be, the roots of the characteristic polynomial need to be less than 1 in magnitude. At least in this implementation of the vector autoregression model, the characteristic roots are the inverses of the characteristic roots that we've been discussing. So anyway, this particular fit of the vector autoregression model suggests that the process is non-stationary. And so one should be considering different series to model this as a stationary time series. But in terms of interpreting the regression model, one can see, okay, to accommodate the non-stationarity, we can take differences of all the series and fit the vector autoregression to the difference series. So one way of eliminating any non-stationarity in time series models, basically eliminate the random walk aspect of the process, is to be modeling first differences. And so doing that with this series, let's see, here's just a graph of the time series properties of the difference series. So with our original series, we take differences and eliminate missing values in this R code. And this autocorrelation function shows us basically the correlations and autocorrelations of individual series and the cross correlations across the different series. So along the diagonals are the autocorrelation function. And one can see that, well, every series is correlation 1 with itself. But then at the first lag, it's positive for the Fed funds and the CPI measure. And there's also some cross correlations that are strong. And whether or not a correlation is strong or not depends upon how much uncertainty there is in our estimate of the correlation. And these dashed lines here correspond to plus or minus 2 standard deviations of the correlation coefficient when the correlation coefficient is equal to 0. So any correlations that sort of go above those, go beyond those bounds, is statistically significant. The partial autocorrelation function is graphed here. And let's see, our time series problem set goes through just some discussion of the partial autocorrelation coefficients and the interpretation of those. The partial autocorrelation coefficients are the correlation between one variable and the lag of another after explaining for all lower degree lags. So it's like the incremental correlation of a variable with a lag term that exists. And so if we are actually fitting regression models where we include extra lags of a given variable, that partial autocorrelation coefficient is essentially the correlation associated with the addition of the final lagged variable. So here we can see that each of these series is quite strongly correlated with itself, but there are also some cross correlations with like the unemployment rate and the Fed funds rate. Basically, the Fed funds rate tends to go down when the unemployment rate goes up. And so this data is indicating the association between these macroeconomic variables and the evidence of that behavior. In terms of modeling the actual structural relationships between these, we need many, well, several, up to about 10 or 12 variables more than these three. And then one can sort of have a better understanding of the drivers of various macroeconomic features. But this sort of illustrates the use of these methods in with this reduced variable case. Let me also go down here and just comment on the unemployment rate. Let's see, or the Fed funds rate. Okay, the Fed. Let me. Okay, when fitting these vector autoregression models with the packages that exist in R, they give us output which provides the specification of each of the autoregressive models for the different dependent variables, the different series of the process. And so here is the case of the regression model for Fed funds as a function of unemployment rate, lagged, Fed funds rate lagged, and CPI lagged. And these are all on the difference scale. When you're looking at these results, what's important is basically how strong the signal-to-noise ratio is for estimating these autoregressive parameters, vector autoregressive parameters. And so with the Fed funds, you can look at the t-values, and t-values that are larger than 2 are certainly quite significant. And you can see that basically when the unemployment rate coefficient is a negative 0.71. So if the unemployment rate goes up, we expect to see the Fed rate going down in the next month. And okay, the Fed funds rate for the lag 1 has a t-value of 7.97. So and these are now models on the differences. So if the Fed funds rate was increased last month, or last quarter, it's likely to be increased again. And that's partly a factor of how slow the economy is in reacting to changes and how the Fed doesn't want to shock the economy with large changes in their policy rates. Let's see, another thing to notice here is that there's actually a negative coefficient on the lag 2 Fed funds term of negative 0.17. And in interpreting these kinds of models, I think it's helpful just to think of, okay, if we have Fed funds sub t, that's equal to minus 0.71 times the unemployment rate sub t minus 1. And then we have plus 0.37 times the Fed funds sub t minus 1. This is a delta. And then minus 0.18, is it? Yeah. Times the Fed funds sub t minus 2. In interpreting these coefficients, notice that these two terms correspond to 0.19 times the Fed funds change one lag ago plus 0.18 times the change in that rate. So when you see multiple lags coming into play in these models, the interpretation of them can be made by considering different sort of transformations, essentially, of the underlying variables. And so this, in this form, you can see that, okay, the Fed funds tends to be, to change the way it changed the previous month, but it also may change depending on the double change the previous month. So there's a degree of acceleration in the Fed funds that is being captured here. So the interpretation of these models, sometimes requires some care, but this kind of analysis is, I find it often quite useful. All right. Okay. So let's push on to the next topic. Okay, so today's topic's going to begin with discussion of co-integration. Co-integration is a major topic in time series analysis, which is dealing with the analysis of non-stationary time series. And in the previous discussion, we addressed non-stationarity of series by taking first differences to eliminate that non-stationarity, but we may be losing some information with that differencing. And co-integration provides a framework within which we characterize all available information for statistical modeling in a very systematic way. So let's introduce the context within which co-integration is relevant. It's relevant when we have a stochastic process, a multivariate stochastic process, which is integrated of some order, D. And to be integrated of order D means that if we take the dth difference, then that dth difference is stationary. And if you are, if you look at a time series and you plot that over time, well, okay, a stationary time series we know should be something that is basically has a constant mean over time. There's some steady mean which that has, and the variability is also constant. With some other time series, it might increase linearly over time. And a series that increases linearly over time, well, if you take first differences, that tends to take out that linear trend. And if there are higher order differencing is required, then that means that there's some curvature, quadratic, say, that may exist in the data that is being taken out. So, so this differencing is required to result in stationarity. If the process does have a vector autoregressive representation in spite of its non-stationarity, then it can be represented by a polynomial lag of the x's is equal to white noise epsilon. And the polynomial phi of L is going to have a factor term in there of 1 minus L, basically the first difference to the d power. So if taking these, the dth order difference reduces it to stationarity, then we can express this vector autoregression in this way. So the phi star of L basically represents the stationary vector autoregressive process on the dth difference series. Now, as it says here, each of the component series may be non-stationary and integrated say, of order 1, but the process itself may not be jointly integrated, in that it may be that there are linear combinations of our multivariate series which are stationary. And so these linear combinations basically represent sort of the stationary features of the process, and those features can be apparent without looking at differences. So in a sense, if you just focused on differences of these non-stationary multivariate series, you would be losing out on the information of the stationary structure of contemporaneous components of the multivariate series. And so co-integration deals with this situation where some linear combinations of the multivariate series, in fact, are stationary. So how do we represent that mathematically? Well, we say that this multivariate time series process is co-integrated if there exists an m vector beta such that defining linear weights on the x's, and beta prime xt is a stationary process. The co-integration vector beta can be scaled arbitrarily, so it's common practice if one has an interest, some primary interest perhaps in the first component series of the process, to set that equal to 1. The expression basically says that our time t value of the first series is related in a stationary way to a linear combination of the other m-1 series. And this is a long-run equilibrium type relationship. Okay, how does this arise? Well, it arises in many, many ways in economics and finance. Term structure of interest rates, purchase power parity. In the term structure of interest rates, basically, the differences between yields on interest rates over different maturities, those differences might be stationary. The overall level of interest might not be stationary, but the spreads ought to be stationary. The purchase power parity in foreign exchange, if you look at basically the value of currencies for different countries, basically different countries ought to be able to purchase the same goods for roughly the same price. And so if there are disparities in currency values, purchase power parity suggests that things will revert back to some norm where everybody is paying on average over time the same amount for different goods. Otherwise, there would be arbitrage would exist. Okay, money demand, covered interest rate parity, law of one price, spot and futures. Let me show you another example that will be in the case study for this chapter. Okay. All right. View. Full screen. Okay. Let's think about energy futures. In fact, next Tuesday's talk from Morgan Stanley is going to be an expert in commodity futures and options, and that should be very interesting. Anyway, here I'm looking at energy futures from the Energy Information Administration. Actually, for this course, trying to get data that's freely available and distributed is one of the things we do. And so this data is actually available from the Energy Information Administration of the government, which is now open, so I guess that'll be updated over time. But basically, these energy futures are traded on the Chicago Mercantile Exchange. And basically, CL is crude, light, West Texas intermediate crude, light crude, which we have here a time series from 2006 to 2000 till basically yesterday. And you can see how it started the period around $60 and then went up to close to 140, and then it dropped down to around 40, and then it's been hovering around 100 lately. The second series here is gasoline, RBOB gasoline. I always have to look this up. This is reformulated blend stock for oxygenated blending gasoline. Anyway, futures on this product are traded at the CME as well. And then heating oil. And what's happening with these data is that we have basically a refinery which processes crude oil as an input, and it basically refines it, distills it, and generates outputs, which include heating oil, gasoline, and various other things like jet fuel and others. So if we're looking at the prices, the futures prices of, say, gasoline and heating oil, relating those to crude oil, well, certainly the cost of producing these products should depend on the cost of the input. So I've got in the next plot a translation of these futures contracts into their price per barrel. Turns out crude is quoted in dollars per barrel, and the gasoline and heating oil are in cents per gallon. So one multiplies, there are 42 gallons in a barrel, so you multiply those previous years by 42, and this shows the plot of the prices of the futures where we're looking at essentially the same units of output relative to input. And what's evident here is that, well, the futures for gasoline, the blue, is consistently above the green, the input, and same for heating oil. And those vary depending on which is greater. So if we look at the difference between, say, the price of the heating oil future and the crude oil future, what does that represent? Well, that's the spread in value of the output minus the input. Right.
The cost of running the refinery.
Okay. So yeah. Okay. So cost of refining. So let's look at, say, heating oil minus CL, and say this RBOB minus CL. So it's cost of refining. What else could be a factor here?
Supply and demand characteristics of each.
Definitely. Yeah, supply and demand. If one product's demanded a lot more than other. So supply and demand. Anything else?
Well, maybe for the outputs, if you were to find the difference between the outputs, it would be something cyclical. For example, in the winter,
Right.
Heating oil is going to get a lot more valuable as gasoline. As people drive less and people demand more for heating homes.
Absolutely, yeah. That's a very significant factor with these. There are seasonal effects that drive supply and demand. And so, we can sort of put seasonal effects in there, sort of as affecting supply and demand. But certainly you might expect to see seasonal structure here. Anything else? Put on your trader's hat. Profit, yes. The refinery needs to make some profit. So, there has to be some level of profit that's acceptable and appropriate. So, so we have all these things driving basically these differences. Let's just take a look at those differences. These are actually called the crack spreads. Cracking in the business of refining is basically the breaking down of oil into, components, products, and on the top is the gasoline crack spread, and the bottom is the heating oil crack spread. And one can see that as time series, these actually look stationary. There certainly doesn't appear to be a linear trend up. But there are, of course, many factors that could affect this. Okay, so with that as motivation, how would we model such series? So let's go back to our lecture here. All right, view full size. Okay, this is going to be a very technical discussion, but it's, at the end of the day, I think, fairly straightforward. And the objective, actually, of this lecture is to provide an introduction to the notation here, which should make it seem like it's a very straightforward derivation process of these models. So let's begin with just a recap of the vector autoregressive model of order P. Okay, this is the extension of the univariate case where we have a vector C of constants, M constants, and matrices phi1 to phi p corresponding to basically how the autoregression of one series depends on all the other series. And then there's multivariate white noise A to T, which has mean 0 and some covariant structure in it. And the stationarity, if the series were stationary, then the determinant of this matrix polynomial would have roots outside the unit circle for complex Z. And if it's not stationary, then some of those roots will be on the unit circle or beyond. So let's actually go to that non-stationary case and suppose that the process is integrated of order 1. So if we were to take first differences, we would have stationarity. Well, the derivation of the model proceeds by converting the original vector autoregressive equation into an equation that's mostly relating to differences, but with also some extra terms. So let's begin the process by just subtracting the lagged value of the multivariate vector from from the original series. So we subtract xt minus 1 from both sides, and we get delta xt is equal to c plus phi1 minus im xt minus 1 plus the rest. So that's a very simple step. We're just subtracting the lagged multivariate series from both sides. Okay, now what we want to do is convert the second term in the middle line into a difference term. So what do we do? Well, we can subtract and add phi1 minus im times xt minus 2. And if we do that, subtract and add that, we then get that delta xt is c plus a multiple of delta xt minus 1 plus this multiple of xt minus 2. So we've basically reduced the equations to differences in the first two terms, or in the current series and the lagged. But then we have the original series for lags t minus 2. We can continue this process with the third, and then at the end of the day, we end up getting this equation for the difference of the series is equal to a constant plus a matrix multiple of the first difference multivariate series plus another matrix times the second difference, all the way down to the pth difference, or the p minus first difference. But at the end, we're left with terms at p lags that have no differences in them. So we've been able to represent this series as an autoregressive function of differences, but there's also a term on the undifferenced series at the end that's left over. And this representation, or this argument, can actually proceed by eliminating differences in the reverse way, starting with the p minus, or the pth lag, and going up. And one then can represent this as delta xt is c plus some matrix times just the lagged series plus various matrices times the differences going back p minus 1 lags. And so at the end of the day, this model basically for delta xt is a constant plus a matrix times the previous lagged series, or the first lag of the multivariate time series, plus various autoregressive lags of the different series. So the formula, these notes give you the formulas for those, and they're very easy to verify if you go through them one by one. And when we look at this expression for the model, okay, this expresses the stochastic process model for the difference series. This difference series is stationary. Okay, we've eliminated the non-stationarity in the process. So that means the right-hand side has to be stationary as well. And well, the terms which are matrix multiples of lags of the difference series, those are going to be stationary because we're just taking lags of a stationary multivariate time series, the difference series. But this pi xt term has to be stationary as well. So this pi xt contains the co-integrating terms, and fitting a sort of co-integrated vector autoregression model involves identifying this term pi xt. And given that the original series had unit roots, it has to be the case that pi, the matrix, is singular. So it's basically a transformation of the data that eliminates that unit root in the overall series. So the matrix pi is of reduced rank, and it's either, well, it ranks 0, in which case there's no co-integrating relationships, or its rank is less than m, and the matrix pi does define the co-integrating relationships. Now, these co-integrating relationships are the relationships in the process that are stationary. And so it's basically, there's a lot of information in that multivariate series with contemporaneous values of the series. You know, there is stationary structure at every single time point, which can be the target of the modeling. So this matrix pi is of rank r less than m, and so it can be expressed as basically alpha beta prime, where these matrices are of rank r, alpha and beta, and the columns of beta define linear independent vectors which co-integrate x. And the decomposition of pi isn't unique. You can basically, for any invertible R by R matrix G, define another set of co-integrating relationships. So, you know, in the linear algebra structure of these problems, there's basically an r-dimensional space where the process is stationary, and how you define, the coordinate system in that space is up to you, or subject to some choice. So how do we estimate these models? Well, rather nice result of Sims, Stock, and Watson. Actually, Christopher Sims, he got the Nobel Prize a few years ago for his work in econometrics, and so this was rather significant work that he did. Anyway, he, together with Stock and Watson, proved that if you're estimating a vector autoregression model, then the least squares estimator of the original model is basically sufficient to do an analysis of this co-integrated vector autoregressive process. The parameter estimates from just fitting the vector autoregression are consistent for the underlying parameters, and they have asymptotic distributions that are identical to those of maximum likelihood estimators. And so, what ends up happening is the least squares estimates of the vector autoregressive parameters lead to an estimation of the pi matrix, and the pi matrix is basically estimated, or the constraints on the pi matrix, which are basically pi is of reduced rank, those will hold asymptotically. So let's just go back to the equation before and just see if that looks familiar here. Okay, so what that work says is that if we basically fit the linear regression model, regressing the difference series on the lag of the series plus lags of differences, the least squares estimates of these underlying parameters will give us asymptotically efficient estimates of this overall process. So we don't need to use any new tools to specify these models. All right. Okay, there's an advanced literature on estimation methods for these models. Johansson does describe a maximum likelihood estimation when the innovation terms are normally distributed, and that methodology applies sort of reduced rank regression methodology and yields tests for what the rank is of the co-integrating relationships. And these methods are implemented in our packages. Let's see, let me just go back now to the well, let's see. Okay, the case study on the crack spread data actually goes through sort of testing for non-stationarity in these underlying series. And actually, why don't I just show you that? Let's go back here. Okay. If you can see this, but for the crack spread data, looking at the crude oil futures, basically the crude oil future can be evaluated to see if it's non-stationary. And there's this augmented Dickey-Fuller test for non-stationarity. And it basically has a null hypothesis that the model or the series is non-stationary, or it has a unit root, versus the alternative that it doesn't. And so testing that null hypothesis that it's non-stationary yields a p-value of 0.164 for CLC1, basically the first, the nearest contract, near month contract of the futures for light crude. And so the data suggests that crude has a distribution that's non-stationary, integrated order 1. And the, let's see, HOC1 also basically has a test for p-value for non-stationarity of 0.3265. So we can't reject non-stationarity or a unit root in those series with these test statistics. So in analyzing the data, this suggests that we basically need to accommodate that non-stationarity when we specify the models. And let me just see if there's some results here. Okay. Let me go up here. Oops. Oh, darn it. I need to use the mouse here. Okay. For this series, actually, there's the case notes will go through actually conducting this Johansson procedure for testing for the rank of the co-integrated process. And that test basically has different test statistics for testing whether the rank is 0, 1, less than or equal to 1, or less than or equal to 2. And one can see that there's marginal, basically the test statistic is almost significant at the 10% level for the overall series. It's not significant with for the rank being less than or equal to 1. And so these results, it doesn't suggest there's strong non-stationarity, but certainly with that non-stationarity is no more than rank 1 for the series. And the eigenvector corresponding to the stationary relationship is given by these coefficients of 1 on the crude oil future, 1.3 on the RBOB, and minus 1.7 on the heating oil. So, so what this suggests is that there's considerable variability in these energy futures contracts. What appears to be stationary is some linear combination of crude plus gasoline minus heating oil. And in terms of why is that, why does it combine that way? Well, there are all kinds of factors that we went through: cost of refining, supply and demand, seasonality, which affect things. And so when analyzed, sort of ignoring seasonality, these would be the linear combinations that appear to be stationary over time. Yep.
Why did you choose to use the futures price as opposed to the spot, and how did you kind of combine the data with actual expiration?
Okay, I chose this because if refiners are wanting to hedge their risks, then they would go to the futures market to hedge those. And so working with these data, one can then consider problems of hedging sort of refinery production risks. And so that's why we looked at that.
Combine them when the actual expiration came?
Okay, well, the Energy Information Administration provides historical data which gives the sort of the first month, the second month, the third month available for each of these contracts. And so I just arbitrarily, well, not arbitrarily, I chose the first month contract for each of these futures. those are the most liquid. Depending on what one is hedging, one would use perhaps longer periods for those. But there's some very nice finance problems dealing with hedging these kinds of risks, and as well as trading these kinds of risks. And traders can try to exploit short-term movements in these. Okay. Okay. All right. Anyway, I'll let you look through these, the case note later, and it does provide some detail, basically on the coefficient estimates, and one can basically get a handle on how these things are being specified. All right. So let's go back. Okay, the next topic I want to cover is linear state space models. It turns out that many of these economic are these time series models appropriate in economics and finance can be expressed as a linear state space model. I'm going to introduce the general notation first, and then provide illustrations of this general notation with a number of different examples. The formulation is we have basically an observation vector at time t, yt. This is our multivariate time series that we're modeling. Now I've chosen it to be k-dimensional for the observations. There's an underlying state vector that's of m dimensions, which basically characterizes the state of the process at time t. There's an observation error vector at time t, epsilon t, so it's k by 1 as well, corresponding to y. And there's a state transition innovation error vector, which is n by 1, which is actually can be different from m, the dimension of the state vector. So we have, in the state space specification, we're going to specify two equations, one for how the states evolve over time, and another for how the observations or measurements evolve, depending on the underlying states. So let's first focus on a state equation, which describes how the state progresses from the state at time t to the state at time t plus 1. Because this is a linear state space model, basically the state at t plus 1 is going to be some linear function of the states at time t plus some noise. And that noise is given by eta t being independent identically distributed white noise, or normally distributed, with some covariance matrix qt, positive definite, and rt is some linear transformation of those which characterize the uncertainty in the particular states. So there's a great deal of flexibility here in how things depend on each other. And right now it will appear, I don't know, just like a lot of notation, but as we see it in different cases, you'll see how these terms come into play, and they're very straightforward. So we're considering simple linear transformations of the states plus noise. And then the observation equation, or measurement equation, is a linear transformation of the underlying states plus noise. So the matrix ZT is the observation coefficients matrix, and the noise, or innovations epsilon t, are, we'll assume, independent, identically distributed, normal, multivariate normal random variables of some covariance matrix HT. And to be fully general, the subscript t means the covariance can depend on time t. It doesn't have to, but it can. These two equations can be written together in a joint equation where we see that the underlying state at time ts gets transformed with t sub t to the state at t plus 1 plus residual innovation term. And the observation equation yt is ztst plus that. So we're representing how the states evolve over time and how the observations depend on the underlying states in this joint equation. And the structure of basically this sort of linear function of states plus error, the error term ut here is normally distributed with covariance matrix omega, which has this structure. It's sort of block diagonal. We have the covariance of the epsilons as the h, and the covariance of RT a to t as RT, QT, RT transpose. So you may recall when we take a covariance matrix of a linear function of random variables given by a matrix, then it's that linear function R times the covariance matrix times the transpose. So that term comes into play. So let's see how a capital S at pricing model with time-varying betas can be represented as a linear state space model. You'll recall we discussed this model in a few lectures ago, where we have the excess return of a given stock, RT, is a linear function of the excess return of the market portfolio, RMT, plus error. What we're going to do now is extend that previous model by adding time dependence t to the regression parameters. The alpha is not a constant, it's going to vary by time, and the beta is also going to vary by time. And how will it vary by time? Well, we're going to assume that the alpha t is a Gaussian random walk, and the beta is also a Gaussian random walk. Okay, with that setup, we have the following expression for the state equation. Okay, the state equation, which is just the unknown parameters, it's the alpha and the beta at given time t. Okay, the state at time t gets adjusted to the state at time t plus 1 by just adding these random walk terms to it. So it's a very simple process. We have the identity times the previous state plus the identity times this vector of these innovations. So st plus 1 is equal to tt st plus rt a to t, where this matrix t sub t and r sub t are trivial. They're just the identity. And a to t is, has a covariance matrix, which is just given by qt sigma squared nu sigma squared epsilon. So this is it's sort of a complex way, perhaps, of representing this model, but it puts this simple model into that linear state space framework. Now, the observation equation is given by this expression defining the ZT matrix as basically the unit element in RMT. So it's basically a row vector, or a row matrix, one row matrix, and epsilon t is the white noise process. Now, putting these equations together, we basically have the equation for the state transition and the observation equation together. We have this form for that. All right. So now let's consider a second case of linear regression models where we have a time-varying beta. In a way, this case we just looked at is a simple case of that. But let's look at a more general case where we have p independent variables, which could be time-varying. So we have a regression model almost as we've considered it previously. Yt is equal to xt transpose beta t plus epsilon t. The difference now is our regression coefficients beta are allowed to change over time. And how do they change over time? Well, we're going to assume that those also follow independent random walks with variances of the random walks that may depend on the component. So the joint state space equation here is given by basically the identity times st plus a to t. That's basically the random walk process for the underlying regression parameters. And yt is equal to xt time transpose times the same regression parameters plus the observation error. I guess needless to say, if we consider the special case where the random walk process is degenerate and they're basically steps of size 0, then we get the normal linear regression model coming out of this. If we were to be specifying the sort of linear state space implementation of this model and consider successive estimates of the model parameters over time, then these equations would give us sort of recursive estimates for updating regressions with as we add additional values to the data, additional observations to the data. Okay, let's look at autoregressive models of order P. The autoregressive model of order P for a univariate time series, has the setup given here. Basically, it's a polynomial lag of the response variable yt is equal to the innovation epsilon t. And we can define the state vector to be equal to the vector of p values, p successive values of the process. And so we basically get a sort of a combination here of the observation equation and state equation joining, where basically one of the states one of the states is actually equal to the observation. And basically with this definition for the state of the vector at the next time point t, that is equal to this linear transformation of the lag state vector plus that innovation term. Adjust the microphone. So the notation here shows the structure for how this linear state space model is evolving. Basically, the observation equation is the linear combination of the phi multiples of lags of the values plus the residual. And the previous lags of the states are just simply the identities times those values shifted. So it's a very simple structure for the autoregressive process as a linear state space model. We have, as I was just saying, for the transition matrix T sub T, this matrix, and the observation equation is essentially picking out the first element of the state vector, which has no measurement error. So that sort of simplifies that. Okay. The moving average model of order Q can also be expressed as a linear state space model. Remember, the moving average model is one where our response variable y is simply some linear combination of innovations Q past innovations. And this state vector, if we consider the state vector just being the innovations, basically Q lags of the innovations, then the transition of those underlying states is given by this expression here. And we have a state equation, an observation equation, which has these forms for these various transition matrices. And for how the sort of innovation terms are related. Okay. Let's see. And this, let me just finish up with examples showing that with the autoregressive moving average model. And many years ago, it was actually very difficult to specify the estimation methods for autoregressive moving average models. But the implementation of these models as linear state space models facilitated that greatly. And with the ARMA model, the setup basically is a combination of the autoregressive moving average processes. We have an autoregression of the y's is equal to a moving average of the residuals and or the innovations. And it's convenient in the setup for linear state space models to think of, or to define the parameter, or the dimension m, which is the maximum of p and q plus 1, and think of having basically a possibly m order polynomial lag for each of those two series. And we can basically constrain those values to be 0 if m is greater than p or if m is greater than q. And let's see, Harvey, in a very important work in '93, actually defined a particular state space representation for this process. And I guess it's important to know that with these linear state space models, we're dealing with characterizing structure in m-dimensional space. There's often some choice in how you represent your underlying states. You can basically reparameterize the models by considering invertible linear transformations of the underlying states. And let me go back here. All right. Okay, in expressing the state equation generally as T sub t st plus RT a to t, this matrix T sub t and st, basically st can be replaced by a linear transformation of st so long as we multiply the T sub t by the invert of that transformation. So there's flexibility in the choice of our linear state space specification. And so there really are many different equivalent linear state space models for a given process, depending on exactly how you define the states and the underlying transformation matrix T. And the sort of beauty of Harvey's work was coming up with a nice representation for the states where we had very simple forms for the various matrices. And the lecture notes here go through the derivation of that for the ARMA process. And that this derivation is, I just want to go through the first example, the first case, just to highlight sort of how the argument goes. We basically have this equation, which is the original equation for an ARMA PQ process. And Harvey says, well, define the first, or the state at time t to be equal to the observation at time t. If we do that, then how does this equation relate to the, basically, this is the state at the next time point t plus 1, is equal to phi1 times the state at time t plus a state at time, or a second state at time t and a residual innovation a to t. So by choosing the first state to be the observation value at that time, we can then solve for the second state, which is given by this expression, just by rewriting our observation, or our model equation in terms of S1t, S2t, and a to t. So this S2t is this function of the observations and a to t. So it's a very simple specification of the second state, just what is that second state element given this definition of the first one. And one can do this process iteratively, getting rid of the observations and replacing them by underlying states. And at the end of the day, you end up with this very simple form for the transition matrix T. Basically, the T has the autoregressive components as the first column of the T matrix, and this R matrix has this vector of the moving average components. So, it's a very nice way to represent the model. Coming up with it was something very clever that he did. But one can see is that this basic model where you have the states transitioning according to a linear transformation of the previous state plus error, and the observation being some function of the current states plus error or not, depending on the formulation, is the representation. Now, with all of these models, what is a reason why linear state space modeling is in fact effective is that their specification is fully specified with the Kalman filter. With this formulation of linear state space models, the Kalman filter as a methodology is the recursive computation of the probability density functions for the underlying states at basically t plus 1 given information up to time t, as well as the density of the joint density of the future state and the future observation at t plus 1 given information up to time t. And also just the marginal distribution of the next observation given the information up to time t. So with so what I want to do is just go through with you how the Kalman filter is implemented and defined. And the implementation of the Kalman filter requires us to have some notation that's a bit involved, but we'll hopefully explain it so that it's very straightforward. There are basically conditional means of the states. S sub t given t is the mean value of the state at time t given the information up to time t. If we condition on t minus 1, then it's the expectation of the state at time t given the information up to t minus 1. So, and then yt, t minus 1 is the expectation of the observation given the information up to t minus 1. There's also conditional covariances and mean squared errors. Okay, all these covariances are termed by omegas. The subscript corresponds to states S or observation Y. And basically the conditioning set is either information up to time t, t minus 1, or t minus 1 in the second case. And we want to compute basically the covariance matrix of the states given whatever the information is, information up to time t, t minus 1. So these covariance matrices are the expectation of the state minus their expectation under the conditioning times the state minus the expectation transpose. That's the definition of that covariance matrix. So the different definitions here correspond to just whether we're conditioning on different information. And then the observation innovations or residuals are the difference between an observation yt and its estimate given information up to t minus 1. So the residuals in this process are the innovation residuals, one period ahead. And the Kalman filter consists of 4 steps. We basically want to first predict the state vector one step ahead. So given the state, our estimate of the state vector at time t minus 1, we want to predict the state vector at time t, and we also want to predict the observation at time t given our estimate of the state vector at time t minus 1. And so at time t minus 1, we can estimate these quantities. Lost it again. Thank you. Okay, at t minus 1, we can estimate these. We can basically predict what the state's going to be and predict what the observation's going to be. And we can estimate how much error there's going to be in those estimates by these covariance matrices. Okay, the second step is basically updating these predictions to get our estimate of the state given the observation at time t, and to update our uncertainty about that state given this new observation. So we basically, our estimate of the state at time t is an adjustment to our estimate given information up to t minus 1, plus a function of the difference between what we observed and what we predicted. And this GT function matrix is called the filter gain matrix. And it characterizes how do we adjust our prediction of the underlying state depending on what happened. So that's the filter gain matrix. So we actually do gain information with each observation about what the new value of the process is, and that information is characterized by this filter gain matrix. You'll notice that the uncertainty in the state at time t, this omega s of t given t, that's equal to the covariance matrix given t minus 1. So it's our beginning level of uncertainty adjusted by a term that tells us how much information did we get from that new information. So notice that there's a minus sign there. We're basically reducing our uncertainty about the state given the information in the innovation that we now have observed. Okay, then there's a forecasting step which is used to forecast the state one period forward, is simply given by this linear transformation of the previous state. And we can also update our covariance matrix for future states given the previous state by applying this formula, which is a recursive formula for estimating covariances. So we have forecasting algorithms that are simple linear functions of these estimates. And then finally, one may have there's a smoothing step, which is characterizing the conditional expectation of underlying states given information in the whole time series. And so ordinarily with Kalman filters are applied sequentially over time, where one basically is predicting ahead one step, updating that prediction, predicting ahead another step, updating the information on the states. And that overall process is the process of actually computing the likelihood function for these linear state space models. And so the Kalman filter is basically ultimately applied in for successive forecasting of the process, but also for helping us identify what the underlying model parameters are using maximum likelihood methods. And so the likelihood function for the linear state space model is basically the log likelihood is the log likelihood of the entire data series given the unknown parameters. But that can be expressed as the product of the conditional distributions of each successive observation given the history. And so basically the likelihood of theta is the likelihood of the first observation times the likely density of the second observation given the first times, and so forth for the whole series. And so the likelihood function is basically a function of all these terms that we were computing with the Kalman filter. And with the Kalman filter, it basically provides all the terms necessary for this estimation. If the error terms are normally distributed, then the means and variances of these estimates are in fact the characterizing the exact distributions of the process. Basically, we're taking, if the innovation series are all normal random variables, then the linear state space model, all it's doing is taking linear combinations of normals for the underlying states and for the actual observations. So, and normal distributions are fully characterized by their mean vectors and covariance matrices, and the Kalman filter provides a way to update these distributions for all these features of the model, the underlying states as well as the distributions of the observations. So that's a brief introduction to the Kalman filter. So let's finish there. Thank you.